In this two-part lesson, I'm going to introduce thermodynamics and thermochemistry to you. Thermodynamics is a science that studies the energy transfers between a system and its surroundings, while thermochemistry is the energy that's required or released during a chemical reaction. We're primarily interested in thermochemistry, but we need to first start with thermodynamics because it has some of the basic principles, ideas, and definitions that we'll need. So what are the different types of energy transfers that occur during a chemical reaction? Well, we can break these up into two different types of energy known as heat and work. The system, first off, is the chemical reaction that's occurring. And the surroundings is everything else that's around the system. The energy transfer known as heat refers to when a hot object transfers thermal energy to a cooler object until the temperatures are the same. So essentially, heat is what you think it is. It's a type of thermal energy. Another form of energy transfer is known as work, which always results from the action of a force through a distance. We're going to define three new quantities known as internal energy, which will be given the symbol U, work, which will be given the symbol W, and heat, which is given the symbol Q. The units of these are joules, and sometimes we'll see the unit calorie. So how does joules and calories relate? Well, 1 calorie is equal to 4.184 joules. And I'll give the abbreviation of J for a joule. The first law of thermodynamics describes how heat and work changes relate to the internal energy. And it distills down to a simple equation that the change in the internal energy is equal to the sum of the heat and the work. So the heat and the work. Now we can think about heat transfer occurring under a variety of different conditions. We could have it occurring under a constant temperature, a constant pressure, or a constant volume. And because the heat value will change depending on the properties depending on the conditions, we say that heat as well as work depend on the path that's taken. And thus, they are not things that we call state functions. A state function is something that is path invariant. But one kind of interesting thing is that the sum of the heat and the work is a state function. It's known as the internal energy. And state functions are really useful in that you can sum them or subtract them to get you a new energy change for a different reaction. And so we want to know what the state functions are. Okay, so in any process where heat is given to the system, is always going to be taken from the surroundings. So you only have the system and you have the surroundings present. So what we can define is that the heat of the system, which is again an energy value, is always going to be the opposite sign but same magnitude of the surroundings. And this is a really important principle that we're going to have to pay attention to. It's this equal but opposite identity. And this is true again for work. So any work that's done by the system is done on the system, is done by the surroundings. Thus, the work of the system is equal and opposite to the work of the surroundings. Let me make that a little more clear. Negative work surroundings. So with these three equations here, we're going to be able to do quite a bit. Okay. One other thing that I want to point out, one other definition, is that in the thermodynamic universe that we're working in, which is defined by the system and the surroundings that we choose, the energy changes of that system and surroundings are going to be equal in magnitude and opposite in sign. So the sum of so one other way we can say this, right? So is that the total energy of the system and the surroundings is conserved, meaning the sum of the surroundings is going to be equal to the negative. So the change in the internal energy of the surroundings is going to be equal to the negative of the change in the internal energy of the system. We can always rewrite this as delta U of the surroundings plus the delta U of the system is equal to the delta U of the universe, which will be equal to 0. It's going to be conserved. There will be no overall change in the energy. It always has to be conserved. All right, so let's look at how energy transfer is done using the experiments. So we have heat transfer and work transfer that are looked at separately here. So if we look at something known as a calorimeter, which we'll talk about more in the next lesson, we have this jacketed vessel, so it's insulated, where inside of this container we have the system, which could be some chemical process that's occurring, and the surroundings, which would, in this case, be something like water. And it's difficult to measure the temperature of the system because the system will generally be present in a smaller amount than the surroundings are. So this thermometer that's in this calorimeter is measuring the temperature of the surroundings. And if the system is exothermic, meaning it gives off energy, gives off heat energy, we'll notice that the surroundings increase in temperature. So what we're doing is we're indirectly measuring the system through the surroundings. And we'll make use of this idea that the heat of the system is just opposite of the heat of the surroundings. And then the opposite process could occur as well, where a system requires heat for it to for the chemical reaction to occur. So the thermal energy will be transferred from the surroundings into the system, and that would be observed by a temperature decrease in the surroundings. We can look at the work transfer that's occurring through the use of a piston, where the piston has a area that can a certain area here where there's an external force being applied on it, and the system itself can push back against that force. We can look at the change in height of the piston to figure out the volume, because the change in height times the area equals the volume change. So essentially here, this delta H times the area, that gives us, times the area, gives us our change in our volume. So here's our change in our volume here. And pistons can be expanded or they can be compressed. So we can look at whether the work is done by the system or done on the system. Because it's a little bit arbitrary as to whether an exothermic reaction should be positive or negative quantity, we need to define this. And this is in chemistry defined simply by the fact that energy that's released by a system is negative, and energy that's absorbed by a system is positive, whether that's work or that's heat. And we can see that in this picture here, when we have the arrows going out of the system, the values are always going to be less than 0. But when we have the values that are greater than 0, that's always when the arrows are going into the system. So if we're specifically talking about heat processes, when the system releases heat, that's exothermic. When it absorbs heat, that's endothermic. When the system does work on the surroundings, meaning it expands, that's going to be a negative value. And when the system is acted on by the surroundings, it's compressed, that gives more energy to that system. Okay, so keep that in mind as we go through the next couple of problems. All right, so I said that we'd start with pressure volume work, and then we'll move into talking more about heat changes. And the idea here is that work is always going to be equal to a force applied over a distance. So we can define that the work is equal to force times a change in the distance. And one thing that we might be familiar with is if I'm going to take an object and raise it, it increases its amount of potential energy. And so that would be equal to the change in the energy is given by the height that I raise an object, and then times its mass times the acceleration due to gravity. For chemistry, we're usually going to be looking at pressure volume work, so we'll define this a very specific way. Oops, what happened to my mouse? Huh? Okay, there it goes. I lost my mouse for a second. Okay, so let's start off by imagining that a gas has a certain pressure when it's confined in a cylinder, and that cylinder has a cross-sectional area A, just like in the picture up here. Okay, so we have some pressure inside the cylinder, and then we have an external force being acted here. Now, the work that's going to be done by the gas in the piston should always be equal to the negative of the external pressure times the area of that cross-sectional area times the change in the height, because area times the change in height just equals the change in the volume. So this is the simpler way of writing the pressure-volume work relationship. And we can define pressure and volume in either pascals or in atmospheres, and volume as either in cubic meters or in liters. Now, the SI units actually use pascals and cubic meters, but for the gas chapter, we were generally using atmospheres and liters. Now, when we plug in those units into this equation, we can get energy in two different values, either in joules or in liter atmospheres. And you can go through the math to figure out how these units compare. But what I would say is that let's just use this conversion factor here so that anytime we're working with pressure and volume in atmospheres and liters, and I want my energy in joules, we can just use this conversion factor. So let's work through one problem here and I'll show you. If I have 2 liters of a gas that's starting at a pressure of 1 atmosphere, and there's one atmosphere of external pressure being applied on it, meaning that the pressures are equal. So there's going to be no compression or expansion to begin with. They're in equilibrium. I then slowly heat that gas under constant pressure until the final volume is equal to 3.5 liters. I want to then know what the work done by the gas is in joules. So we're essentially expanding this container so that the volume is greater. And I can use this equation here. So the external pressure times the change in volume. And the change in volume is going to be equal to the final minus the initial volume of the system. So the external pressure is going to be kept the same at 1 atmosphere. And then the final volume is 3.5 liters. And then the initial volume was 2.0 liters. Okay, so when we work this out, we find that the work energy is equal to negative 1.5 liter atmospheres, because the units here are just liters times atmospheres, and that is not equal to 1 joule. So what we need to do is use this conversion factor, that 1 liter atmosphere is equal to 101.325 joules. And so this comes out to be, I think I did it already, this is negative 152 joules. And this could be part one of a two-part problem, where you then have to determine the heat transfer that's occurring and find the internal energy change of the system. There's a couple problems like this on your homework. All right, so let's go and start moving over to heat transfers. And heat transfers that occur at constant pressure, meaning usually at atmospheric pressure, are known as the enthalpy change. So we discussed above that heat is not a state function, meaning it depends on the process at which we carry it out. However, if we carry out a reaction at constant pressure, the heat change actually is a state function. And we define this as this new term called the enthalpy, which is given the letter H as its abbreviation. So we can define enthalpy as equal to the internal energy plus the pressure volume, the pressure times the volume. And when we have a chemical reaction that occurs at constant pressure, so that we're going to look at the change now in the enthalpy, that would be equal to the change in the internal energy plus the pressure, which we're going to say is constant here, times the change in the volume. We can substitute in the first law of thermodynamics, and that was equal to the change in internal energy is equal to the heat plus the work, and this subscript here means it's at constant pressure. So I can replace in the internal energy here with QP plus WP. And then we can substitute in that the work is equal to the negative of the pressure times the change in volume. So then the change in the enthalpy becomes the heat at constant pressure plus negative P times delta V plus P times delta V. And then we can see here that these two terms combine to give us 0, so that the enthalpy, or the change in enthalpy, is just equal to the heat at constant pressure. Now this derivation here is a little tricky, but the idea here is that the heat at constant pressure is a state function. And it doesn't depend on the path that's taken. So that's how we're going to pretty much use enthalpy for the remainder of these two lessons. Okay, so we can, what did I write here? The energy involved or absorbed as heat at constant pressure is the enthalpy, and this is a state function, meaning these values are repeatable and only dependent on the chemical reaction involved, not on the process. And this is very useful to know that. Okay, so let's look at the enthalpy change for a couple of our reactions. And we're typically going to give these energy changes in terms of kilojoules, because chemical reactions give off a lot of heat, or they require a lot of heat. And so 1 joule is not very much. And we'll typically write this enthalpy change to the right of a chemical reaction. So we'll kind of see it like this. And for each of the following, the enthalpy change is going to be written such that the number of moles of reactants and products taking part in this reaction are going to be given by the coefficients in the equation. Let me show you how this works. So let's calculate the enthalpy change for two different reactions when we have 1 gram of the underlying substance that's consumed or produced. So if I have a synthesis reaction between sodium and oxygen, I form sodium oxide, and I have a balanced chemical reaction. And the enthalpy of this reaction is negative 828 kilojoules for the amounts for the reaction as it's written. So that means that we have to pay attention to the coefficients here. Okay, so let's start off by trying to find this enthalpy change. We have 1 gram of the underlying substance, that would be sodium oxide, Na2O. And in order to figure these enthalpy changes out, I need to put them into terms of moles. Okay, so let's find the molar mass of sodium oxide. That's 61.98. And then what we can do is use this enthalpy of this reaction. And this is negative 828 kilojoules for however many moles of the substance that's written, of each of these substances. So it's negative 828 kilojoules for every 4 moles of sodium, for every 1 mole of oxygen, or for every 2 moles of sodium oxide. Okay, so there's negative 828 kilojoules for every 2 moles of sodium oxide, because we have to pay attention to how this reaction is written. So I'm going to highlight that just to point out that little difference. And this is the tricky part about thermochemistry. We got to divide here by 2. And let me pin this. All right. So this comes out to be negative 6.68 kilojoules of energy. And because this value here is negative, that means that this is an exothermic reaction. That's how much energy is going to be given off when that much sodium oxide is produced. So when we produce 1 gram of sodium oxide, we will get negative 6.68 kilojoules of energy. Okay, how about this chemical reaction? Maybe pause the video and try this one and see if you can get it. Here we want to take hydrogen, combine it with carbon monoxide to form this molecule, which is known as hydrogen peroxide, and carbon. So we'll start with 1 gram of carbon monoxide, CO. Convert that into moles. And then we want to pay attention to how the chemical reaction is written. So for every 33.3 kilojoules of energy that's required, that's for every 2 moles of CO. So this reaction is endothermic. It requires energy to occur. So how much energy do we need to react 1 gram of carbon monoxide? We need 0.594 kilojoules. So we can work with energy just like we work with mass when we have these values here. And these values are all usually determined experimentally, although I will show you in the next lesson how we can derive some of these energy values, but we still, again, need to know some empirical values to figure them out. Okay, how about if we look at the delta H of reaction A when it's written this way? Well, this is just this reaction, but the coefficients are divided by 2. And when I was introducing stoichiometry, I always was having us write out the chemical reactions with whole number coefficients. However, this is still a valid balanced reaction. A half a mole of oxygen can react with 2 moles of sodium to give us 1 mole of sodium oxide. And sometimes this is the preferred way to write it in thermochemistry. But one thing you want to pay attention to is because the enthalpy of a reaction, although it's a state function, it's also a extensive property. So delta H is extensive, meaning it depends on how much you have of it. So this delta H value is going to be half of what it was up above. So it's going to be negative 828 divided by 2. So it's not intensive like density, it's extensive. Depends on how much you have. Okay, how about this reaction where I take the reaction from C and I flip the reaction. So now the sodium oxide, instead of being produced, is being consumed. So we have the decomposition reaction. Well, delta H of this reaction is going to be the opposite of it. So it's going to be negative 414, the value from above, times negative 1. So it's going to be positive 414. So this is the opposite process. So delta H depends on the direction of the reaction. Okay, and sometimes you'll see that the units are written as kilojoules per mole. You'll do the same type of reaction. So you might see this as written as kilojoules per mole. But just pay attention that it's per mole of however many of that thing you're working with, its coefficients. Okay, let's introduce a few more definitions because we already, don't have enough to worry about. When an enthalpy change occurs at standard conditions, we'll additionally add this symbol, this degree symbol to it. So if you see delta H naught of the reaction, that refers to the standard enthalpy change of a reaction. Delta H naught for short. What are the standard conditions? Well, for a solution, like some solute dissolved in a solvent, it's typically 1 molar. For a standard temperature, it's generally 25 degrees Celsius, but that depends on the reference book you're working with. So sometimes it's 20 degrees Celsius. You want to pay attention to that. And then the standard pressure is typically 1 bar. It could be 1 atmosphere. So just pay attention to that as well. This is needed because delta H depends upon the different conditions. So if I increase the temperature of a chemical reaction, it can either cause it to be more exothermic or less exothermic, depending on how we change the temperature. All right, some other common symbols that we're going to be seeing are the standard enthalpy of a combustion reaction. So any reaction that combusts will sometimes be written like that way. The standard molar enthalpy of formation, which we'll talk about in the next lesson. These are reactions when we have 1 mole of a product that's formed from its simplest elements. So that would be like this reaction. This could be written as a delta H of formation reaction because it's 1 mole of sodium oxide from its simplest elements, which would be sodium and oxygen. And then we can also refer to a heat process of a physical process like fusion or vaporization. Fusion just refers to the melting process of a solid to a liquid. And whenever we have a melting of an object, there's actually a constant temperature at which this occurs. And this is referred to as the latent heat because there's no temperature change in the thermometer. So it appears as if nothing's occurring, but there's actually a lot of heat that's required for that reaction to occur, that phase transition. And then vaporization is just given by delta H of vaporization. And this value is always greater than the delta heat of fusion. It usually takes a lot more energy to vaporize something. We'll talk more about that in the next lesson. Okay, so done with those definitions. Let's look at Hess's law, which is a really important way to look at how enthalpy changes and their property being a state function can be used to figure out new chemical reactions. So if we have two chemical reactions that are done in tandem and we want to know what the new overall reaction enthalpy is, we can simply sum the delta H values of those two different reactions, or if we might have 3 or 4 reactions that are occurring, we can sum all those together. We just need to make sure that we sum them together in the right order. So we saw above that the enthalpy change of a reverse reaction is simply the reverse of the forward enthalpy. And we also saw that when we multiply or divide the coefficients by a factor, we need to do the same thing to the enthalpy change. These are summarized in the 3 laws of Germain Hess, which he published in 1840. And we can see the addition of 2 or more chemical reactions, the multiplication of a chemical equation by a factor of n, and the reversing of a chemical equation. So the new one we're adding is this first one here. Okay, so let's go through a couple of practice problems with this. If I have copper and I have chlorine gas, I can form copper chloride, and that energy at standard conditions is equal to negative 220 kilojoules per mole. We can also combine copper and chlorine to form copper 1 chloride. So this first one's copper 2 chloride. And that has a different enthalpy change. Now, if I want to calculate the value of the enthalpy reaction to form copper 1 chloride, starting with copper 2 chloride and copper, I can take these 2 reactions and combine them to get this new delta H value. What we'll do is we want to make sure that when we add these 2 reactions together, all the reactants sum to equal the reactants on the left side here, and all the products sum to equal the products on the right side here. Now, as it's written, that's not going to occur. So let's do some color coordinating. That's how I typically do all these problems. It's really quite simple. You have copper 2 chloride here. That's a reactant in the overall reaction, but it's a product here in the first reaction that's written. So that means that I'm going to need to rewrite this first reaction. So I'm going to need to reverse it. We'll apply this principle, reversing a chemical reaction. So copper 2 chloride, when you decompose it into copper and chlorine, the delta H value for this is going to be equal to positive 220.1 kilojoules per mole. Okay. All right, so now that that's on the right, on the correct side, that's good. Let's take a look at this other reaction. Well, this other reaction, as it's written, has copper chloride on the right. That's good, and it has 2 of them, which we need 2 of them. Okay, so let's see what happens if I just add this other reaction to this one. So I'll have copper and chlorine and 2 copper chloride. And the delta H of this reaction is equal to negative 137.2. And so let's add them together. Well, what we see when we try to add them is that chlorine is on both sides of the reaction. And so kind of like when we're writing a net ionic equation, these are acting as spectators. and they don't show up in the overall final reaction. And then when we add the coppers together, there's 2 moles of copper in the bottom reaction, but there's only 1 mole of copper in the top reaction. So that simplifies down to 1 copper as a reactant. And this is only possible because enthalpy is a state function. And we can see that we get the reaction that's required. And so the delta H value of this reaction should be equal to the sum of those two. And it's a positive 82.9. Okay, so that's Hess's law when we have 2 different reactions that occur. Let's look at an example where we have 3 different reactions that occur. So this is where I think it's good to practice, these problems. Just pause the video and try them on your own, and then check to see if you did it correctly. Okay, so I'm going to color coordinate this. I want to get this overall reaction. So carbon disulfide, oxygen forming carbon dioxide and sulfur dioxide. Well, this reactant, carbon disulfide, only appears in one reaction. And that's what we want to pay attention to, is the reactants and products that just occur in one reaction. And what we can do is usually solve the problem that way. So this one here shows up right there. It's obviously on the wrong side. So what I'm going to say is we're going to need to flip this enthalpy to give us negative 87.9. I'll deal with the math in just a minute. Okay, so let's look at another reactant, oxygen. Well, oxygen, that occurs in multiple different spots. So I'm going to pay attention to that last. What about carbon dioxide? Well, that shows up just in this reaction, and it shows up on the right side and has the correct number of those. So we don't need to modify that formula. And then the last one we have is sulfur dioxide, and that shows up again only in one spot. However, it has the wrong number of coefficients. So we want to pay attention to that. So what we're going to need to do here is multiply this one by 2. And when we multiply the coefficients by 2, we multiply the enthalpy by 2. Okay, so let's go and write out our new reactions, and let's see if they sum to give us this overall reaction. So for some of these, I might, well, actually, I'm going to keep the states of matter here because sometimes you'll do one of these problems and it will have different states of matter. So I'll keep them in. And what I think I want to do is leave some space here. Okay, so this delta H value stays the same. It's negative 393. And then this next reaction, we're going to multiply it by 2. So we'll have 2 moles of sulfur. Okay, here we need to multiply the enthalpy by 2 because I just modified the chemical reaction. Okay, negative 593.6. Okay, and then what about this last one? We're going to flip this reaction. So if I flip this reaction, we'll flip the enthalpy. So now carbon disulfide is on the left, and carbon and sulfur are on the right. and we flipped it, so this becomes negative now, negative 87.9. And I think I'm going to highlight this just to point out here what we changed here. And then in the above one here, we changed this value. Okay, let's take a, oh wow, I fixed it. Okay, let's take a look at how these combine together. First thing I like to look for is the things that are on both sides. So if I add these two reactions together, those will cancel out. I said that we shouldn't worry about the oxygen in case, until the end. And when we add these together, we do get 3 moles of oxygen. So that works out. And then what else? Can we cancel anything else? We can cancel out the carbon, okay, because carbon should not appear in the overall reaction. Now, it's often very difficult to figure out the enthalpy change of a reaction given, for certain reactions, just because they're hard to occur, and especially for like chemical processes that are endothermic. Exothermic reactions are very easy to measure the heat change, but sometimes endothermic reactions are difficult. And so this is one common way that chemists will find these values. Okay, so the delta H of this reaction is going to be equal to sum of all those. Just sum them all. Very, very simple. Okay, negative 1,075. All right. So you can also flip and multiply an equation. And here's a tricky one. So let's try this one. This will be our last example for today's lesson. Using only these equations, let's calculate the molar heat of formation of nitrous acid. And the molar heat of formation, we're going to have to write this equation out. What is the molar heat of formation? Well, if we again look back at this definition I gave us, it's the reaction where 1 mole of the product is formed from its simplest elements. So usually these reactions are not able to be done. So that's why you would have to use Hess's law to figure this out. So 1 mole of the product is formed would be HNO2 on the right side. And then what would the simplest elements of each of these be? Well, it'd be hydrogen, nitrogen, and oxygen. So hydrogen in their simplest elemental state as well. So hydrogen would be a gas, nitrogen would be a gas, and oxygen would be a gas. Okay, now one thing we have to pay attention to is when I balance this reaction, I want to make sure that this stays as a 1, okay? Because I need 1 mole of that. So to get 1 hydrogen on the left side, we'll multiply this by 1/2. To get nitrogen to be 1 on the left side, again, we'll multiply this by 1/2. And then the oxygen will stay the same as O2. Okay, so because this molar heat of formation has fractions in it, it can be a little bit tricky to do the math on this. Sometimes what I'll do, if in a problem like this, is I'll actually calculate the molar heat of formation times 2, and then I'll like divide the final answer by 1/2 or by 2 to get my final answer. Let's go ahead and do it that well. I think we can try to keep it this way. Let's see if this works out for us. Okay, so to begin with, we have 4 different reactions, and let's try to identify where our product is. So if I have nitrous acid, HNO2, that shows up right here in this reaction. So if I combine ammonia and nitrous acid, I can get ammonium nitrite. And ammonium nitrite has a delta H of negative 37.7 kilojoules. Okay. Now, there's no other reactions here that have nitrous acid in them. Instead, they deal with ammonia, and this other one deals with ammonium nitrite. And they break down into nitrogen and water. And then we have the electrolysis of water equation, and then we have the breakdown of ammonia equation. So what we're trying to do is find 3 different reactions that can break these down into simpler substances. And hopefully those other reactants that are intermediate to the production of nitrous acid get eliminated when we work through this process. So let's see here. We have H2. Okay, H2 occurs in 2 different spots, here and here. And then we have N2 that occurs here and here. And then we have oxygen, which occurs here. And okay, that's the only spot that one occurs. Okay, that's good. So let's start with the yellow and the blue, and then we can see to make sure that the ammonias cancel out, and then the ammonium hydroxides cancel out. All right, so what I'm going to need to do here is I'm going to need to flip this reaction. And then for the oxygen, we're going to need to keep this one the same. And then we'll need to figure out what we need to do with these two after we write these. So ammonium nitrite. All right, and the next thing we should do is let's go ahead and write out our delta H values. So we flipped this, so this becomes a positive now, 37.7. Okay, the oxygens, we're going to keep this reaction the same down here. 2H2 plus oxygen gives us 2H2O. And that's still negative 571 kilojoules. Okay, and then for the next 2 reactions, how do we combine? Let's look at the third reaction now. So we have 1, 2, 3, 4. If we look at reaction 3, because we want to combine these 2 together to give us 1/2. So we'll need to multiply reaction 3 by something so that when we add together the hydrogens, we get 1/2 hydrogen. We also want to make sure that the ammonias cancel as well. So if I need to have this reaction kept in the same way so that I have ammonia on the left and on the right. What I will do is I'm going to multiply this one by 1/2. And I'll show you why. So I'm going to multiply it by 1/2 and I keep it the same, like same orientation. So this will become NH3. And then we'll have 1/2 N2 and 3/2 H2. And then my delta H value here is going to be decreased in half. Okay, 84.95. Okay, and then what we can kind of see here is that the ammonias already cancel here, and that's helpful. And then the hydrogens, on this side I have 1.5 of them, and on this side I have 2 of them. So that means that these will end up canceling, and this will give us 1/2. Okay, well, that's what we need. Okay, perfect. What else can we eliminate so far in this? Nothing else. So now we have to look at chemical reaction number 1. And here, this is where we're going to get rid of the water, because water doesn't show up in our molar heat of formation equation. So we'll need to flip this one, and that will keep the number of moles of water the same, and it will cancel them out. So I'm playing this game of flipping and multiplying just to cancel out different values we don't need. And then on the right side, we will have NH4, NO2, ammonium nitrite. And the delta H of this one will be negative, the negative of the negative, so positive 320.1 kilojoules. Okay, now let's look at how the nitrogens and waters are dealt with. So these end up canceling. And then the ammonium nitrites cancel. And then for the nitrogen, that's our last part. So we have 1/2 on the right side, and we have a full on the left side. So those cancel, and this gives us 1/2 then, which is exactly what we need for this chemical reaction. So we sum all these together, we'll get 1/2 H2, 1/2 N2, 1 full oxygen, and then on the right side, we have our nitrous acid. And then overall, this reaction can be summed from those. I'll make sure I flipped everything, multiplied by 1/2, kept that the same. Yeah, I think that should be right. Okay, negative 128.85, and we only have 3 sig figs here, 1 decimal place really, because we're adding these. So negative 128.9. We're going to use the addition rule here. Okay, and that's the delta H. And these are at standard state conditions, so we'll want to use the not symbol. And this is a formation enthalpy, so we can write the word formation down there. And there you have it. So that's Hess's law. Hess's law, I would suggest practicing some of these problems from your textbook. Some of these I found from an online website, I think on chemteam.info. You can find some of those additional problems there. And then we'll wrap up lesson 21 next week, and that'll be the end of the content from this course. All right, so look forward to talking to you about that, and have a great day.